Welcome to The Explainer. Today, we're going to tackle what might be the most famous equation in history, E equals mc squared. I mean, you see it everywhere, right? But what does it actually mean? And why is it so incredibly important for how we understand the entire universe? So let's just start with a really big question. Why is this simple, elegant little formula basically the biggest roadblock to our dreams of zipping around the galaxy? Believe it or not, the answer is packed right into these 5 little characters. When Albert Einstein published this back in 1905, he wasn't just showing a link between energy and matter, he was also revealing a fundamental cosmic speed limit. And that speed limit has some pretty profound consequences for space travel. Okay, so let's break this thing down piece by piece and see exactly how it works to set this universal speed limit. First up, we've got E. That, of course, stands for energy. And we're talking about the total energy of an object. That's a combination of the energy it has just sitting still, plus the energy it picks up from moving. Next, we have M for mass. The easiest way to think about this is just the amount of stuff an object is made of. The more mass, the more stuff, and the more energy is locked up inside it. And finally, C. Now, this is a big one. It's a constant, and it represents the speed of light in a vacuum. It is the absolute fastest that anything can travel anywhere in the universe, full stop. But here's the kicker. The equation doesn't just use C, it uses C squared. And when you do that, you get an absolutely astronomically huge number. What this is telling us is that it takes a truly enormous amount of energy to get even a tiny bit of mass moving anywhere close to the speed of light. Because of that immense energy requirement, it turns out that only particles with 0 mass, like photons, the particles that make up light, can actually travel at this speed of light. But is that the whole story? Well, it turns out there's another little piece to this puzzle. You see, to get the full picture, we really need to look at a slightly more detailed version of the equation, the one that physicists often use. They add one more variable to the mix. This symbol right here, the Greek letter gamma. And this is where things get really interesting. This gamma is something called the Lorentz factor. It's kind of the secret ingredient that really explains why this cosmic speed limit exists. It's a way to mathematically describe how an object's mass, its length, and even its experience of time all start to change as it moves faster and faster. And here's where it gets a little wild. The calculation for the Lorentz factor involves division. But as an object gets closer and closer to light speed, the number you have to divide by gets smaller and smaller. So if an object with mass were to actually hit the speed of light, you'd be trying to divide by 0. And you just can't do that in math. The equation simply breaks. And that mathematical breakdown represents a very real, very unbreakable physical barrier. But what does it really mean for the math to break? To really understand that, we have to stop thinking about space and time as 2 separate things and start thinking about the actual fabric of the universe itself. It was actually Einstein's old professor, Hermann Minkowski, who had this profound realization. He saw that space and time weren't 2 different things at all, but a single 4-dimensional system he called space-time. And every single object in the universe is constantly traveling through it. And this is just a brilliant way to think about the trade-off. If you're sitting perfectly still, you're actually traveling 100% through the time dimension. But the faster you move through space, the slower you have to move through time. It's a trade-off. So if you could somehow hit the speed of light, you'd be moving 100% through space, and for you, time would effectively just stop. Okay, so this cosmic speed limit seems pretty absolute. But science is always full of surprises, and it turns out there are some very interesting loopholes hiding in the fine print of that famous equation. Remember, the C in E equals mc squared is specifically the speed of light in a vacuum. That's key, because light actually slows down when it passes through different materials. For instance, when light travels through water, its speed drops by about 25%. And this creates a really fascinating opportunity. In labs, scientists can actually shoot particles like electrons through water at speeds faster than the light moving through that same water. Now, this doesn't break the universal speed limit, C, but it does mean the electron is outrunning the light in its immediate area. And when that happens, it creates a kind of optical sonic boom, this ghostly, beautiful blue glow known as Cherenkov radiation. So while we can't travel faster than light in a vacuum, that has never stopped scientists from imagining what would happen if we could. What would the universe even look like from such an impossible point of view?
Well, if you were on a spaceship getting close to light speed, Your perception of reality would just warp dramatically. The stars in front of you would look intensely blue, while everything to the side and behind you would stretch out and shift toward red. Your entire field of view would become this bizarre, kaleidoscopic tunnel of light. And that brings us to our final provocative thought. If you could somehow find a way to break this ultimate barrier, to go faster than the speed of light in a vacuum, what would that even mean? Could it be a form of time travel, letting you rewrite our basic understanding of cause and effect and of physics itself? It's a question that continues to inspire scientists and dreamers alike.